Two isolated particles, suspended in a total vacuum, can violently accelerate away from each other without ever making physical contact. This action at a distance is driven by the electrostatic force. It is the invisible mechanical interaction that governs how charged particles push and pull on one another across empty space. To study this mechanism purely, we strip away real-world complexities and look at point charges. A point charge is an idealized mathematical model of a particle that possesses an electric charge but occupies strictly zero volume in physical space. Observation gives us a baseline rule for how these charges interact. Homogeneous or like charges, whether both positive or both negative, will always repel each other. The direct corollary is that heterogeneous or opposite charges, one positive and one negative, will always pull toward one another in attraction. But observing attraction and repulsion is only a qualitative starting point. Our objective is to derive Coulomb's law from first principles, establishing a mathematical model that calculates the exact vector direction and precise magnitude of this force. Mastering electrostatics is the process of building a rigorous geometric architecture to predict the behavior of the physical universe. We begin building this model by isolating two separately charged spheres in a three-dimensional plane. Before calculating math, we find the absolute geometric center of each sphere. The interaction is anchored here, giving us a strict geometric constraint. The electrostatic force vector operates exclusively along this single, straight linear axis. It cannot deviate or curve. With the shared axis established, we can map the specific forces acting on each individual particle. Vector F12 is the mechanical force exerted on the first particle by the second. On the opposite side, F21 is the reciprocal force. By Newton's third law, these two vectors are perfectly equal in magnitude, but point in exact opposite directions. Vector geometry dictates exactly where the force points. Now we must construct the mathematical framework to calculate exactly how much force is actually moving along that line. The magnitude of this force is governed by two independent physical variables. The first is the absolute size of the charges themselves, which we label Q1 and Q2. This split-screen graph plots force on the y-axis against charge product on the x-axis. As we scale up either individual charge, the total interactive force scales alongside it. Formally, the force is directly proportional to the product of the two charges. The second physical variable is the distance or spatial separation between the two geometric centers, denoted by the variable d. Plotting force against distance shows rapid decay as space expands. This follows an inverse square law, dropping off exponentially. Doubling the distance doesn't halve the force, it cuts it to 1/4. Mathematically, force is inversely proportional to the square of the distance. The total magnitude of the electrostatic force is constantly balancing these two physical rules: the multiplying power of the charge product pulling it upward, and the exponential decay of physical space aggressively dragging the total force downward. We are left with two independent proportional rules that must operate simultaneously to determine the true force. To combine them, we use the theorem of joint variation. It states a dependent variable relying on multiple independent variables is proportional to their combined product. Multiplying our properties yields a unified relationship. Force is proportional to Q1 times Q2 divided by d squared. However, there is a practical limitation here. Proportionality describes the ratio of change. If distance doubles, force quarters, but it cannot output an absolute, measurable real-world value. To evolve this into a practical engineering tool, we have to convert this mathematical proportionality into an absolute equality. Converting a proportionality into a strict equation requires replacing the proportional sign with an equal sign and a constant. Here, that constant is k. The Coulomb constant acts as the mathematical bridge linking theoretical ratios to standardized units of physical measurement. In the older CGS unit system, this constant is simply valued at 1 in a vacuum, which makes the formula highly streamlined. But in the universally adopted SI system, k is expanded into a more complex form, 1/4 pi epsilon naught, yielding a value of roughly 9 times 10 to the 9th. The critical variable hidden inside this expanded constant is that denominator symbol, epsilon naught. Epsilon naught is formally defined as the permittivity of free space. In physical reality, permittivity is the specific metric of how much resistance the vacuum of space itself offers to the propagation of an electric field. Therefore, the constant K is the physical footprint of the universe's medium, embedded directly into the equation. This gives us the final SI equation of Coulomb's law. First, the multiplied charge product drives the force magnitude upward. Second, inverse square spatial decay aggressively drives the force downward as objects separate. Finally, center-to-center vector geometry dictates direction, scaled absolutely by the vacuum permittivity. By unifying charge, geometry, and space, Coulomb's law serves as the bedrock of electrostatics. It allows us to mathematically model and manipulate the flow of force, scaling from the microscopic layout of atomic structures to the massive power systems of industrial capacitors.